María here is going to talk to us about magnetic fields and planetary nebulae.
Okay. Okay, hello everybody. I'm going to talk about a work that I made in collaboration with Franco Leone from the University of Catania and Roberto Corrari and Rafa Manso here in the IEC. The subject is the role of magnetic fields shaping planetary nebula. So, this is just a schematic representation of the evolution of an intermediate mass star. As everybody knows, the late stages of intermediate mass stars, the outer layers are ejected and the nucleus started to collapse. This mass ejection is done in two phases, first with a slow wind and then with a fast wind in the protoplanetary nebula stage. At the end, we have in the white dwarf in the center of our planetary nebula. And as you can see, as expected from a spherical object, all this mass loss is done in an isotropical way. So we end up with very nice examples of planetary nebula. We have spherically symmetric shapes, like this one here. But this is not a rule, but this is an exception, and most planetary nebula are not spherically symmetric, but they have much more complex shapes, most of them presenting axisymmetric shapes with clear axis of symmetry, presenting bipolar structures like this one here, and this one here, and also much more complex shapes presenting several axes of symmetry like this one here. Some of them also present very nice phenomena like very collimated jets, like this one here, and not. Well, está muy brillante, ¿no? Well, this example here is a very nice one to illustrate what I wanted to show, is that in the early phase of AGB, the slow wind is ejected isotropically, forming these halos around the nebula. But then the mass loss is done in a non-spherical asymmetric way. So we can see jets and much more complex features. So what happens between this AGB phase and this protoplanetary nebula phase that makes the winds become collimated or non-spherically symmetric? What is clear is that there is any mechanism that is still not known that breaks this symmetry. And of course, the most obvious candidates to break any symmetry are the binarity, or the evolution of two very close binary stars that form a common envelope, which dynamics is still not very well known, that can create accretion disks and complex phenomena that eventually can collimate the wind. And another candidate is the magnetic field, which in this case will act as a collimator of the ejected material. Imagine, for example, a very simple structure of a dipole. In this case, the mass loss will be collimated around the poles where the magnetic field lines are open. And as I told you, in this work, we are going to focus in the role of magnetic fields shaping planetary nebula. And of course, the first thing to do is just detect if, in fact, there is any magnetic field in the planetary nebula. It is difficult to detect magnetic fields in the nebula, but it's a bit more simple to detect magnetic fields in the central star. So first thing to do is to look at the central stars if there is any magnetic field in there. And to detect a magnetic field, we are going to to use the Zeeman effect in spectral lines. In the presence of a magnetic field, the atomic levels are non-degenerated, so the transition between magnetic sublevels occur for different energies. This is a very simple description of an atomic level, an atom in a classical, in a classical way, in which it can be described as three harmonic oscillators. One of these is oscillating linearly polarized along the magnetic field direction, and the other two are circularly polarized processing the magnetic field. And these two circular polarized oscillators are occur for energies which are displaced by the Larmor frequencies, which is depends on the magnetic field. And when we observe intensity, which is nothing but the addition of two orthogonal states of polarization, we end up with profile like this one, for example, either in emission or in absorption. In the case that there is no magnetic field, we will have profiles like this one, which are broadened by thermal and rotational effects, etc. But when we have a magnetic field, we have a broadening of the spectral line due to the Zeeman splitting. So in principle, if magnetic field dominates, we can measure magnetic fields in intensity. But of course, it is not very usual, and it's very difficult to disentangle magnetic from thermal effects in spectral lines. So to reliably determine measure magnetic fields, we have to go to measurements of polarization. This is the definition of the circular polarization, the Stokes-B profile, which is nothing but the difference between the two circular polarized oscillators. And of course, if there is no magnetic field, there is no Stokes-B profile. But if there is a magnetic field, there is a profile like this one, an antisymmetric profile. So if we find these kind of profiles in Stokes-B spectra, we are sure that there is a magnetic field in there. We also can measure linear polarization, which has profiles like this one, symmetric profiles, but this is too faint to be observed, and we focus on the observation of circular polarization. Well, the first work to claim that there are magnetic fields in the central stars of planetary nebula is the one by Jordan et al., who observed 4 central stars of planetary nebula and found very strong kilogauss fields in 2 of them. These two ones. This is the intensity spectra. You can see that it's an absorption spectra. It's typical for it's the stellar spectra, and the contamination in the nebula is not very. Well, it's not too much. There is only a few spectral lines here, and it was chosen for that reason. And this is the circular polarized spectra. Can we change the luminosity of the? It's too bright. Okay, this is the circular polarized spectra, and well, as you can see, these are different spectral lines, and the amplitude of this the signal is 10 to the minus 3. But as you can see, apart from the fit they put on the spectra, there is pure noise. But even if this is pure noise, they decided just to fit a magnetic field in the spectra, and of course they got you can see such a different results for different spectral lines. So they got minus 500 Gauss and 2,500 Gauss. It's like crazy, because this is the hydrogen. So in principle, if there is a magnetic field, at least the same species, the same atomic species, should measure consistent magnetic fields. Then what they did is just, as their result, they average all these results for different spectral lines, but they weighted the results using the depth of the lines, that in principle has nothing to do with the sensitivity to the magnetic field, but they did it like this, and they got 1 kilogauss in the central star. And of course they also made an average of the errors. This is the reason why the error is much more slower than the individual errors. Okay. Well, when we saw this result, we were like, this can be really put in doubt, because if there is a strong kilogauss magnetic field, we are sure that we can measure. And we are sure because we measure Stokes V signal in stars having kilogauss magnetic fields. This is an example of an AP star having a kilogauss magnetic field. This is the Stokes V profile, so the antisymmetric shape expected. And you can see that the shape is common in all the profiles. This is what we call the null spectra. Is just a modulation that should be 0, and this gives us an idea of the systematics in our measurement. So, as this work was also very important work in the field, we think we can put it in doubt very easily. We decided to repeat their observations using the very same instrumentation, but in our case we could increase the spectral resolution, and also we reached a higher polarimetric sensitivity. And well, we developed also some tools to retrieve the magnetic field consistently. And these are our results for the 2 planetary nebula. This is the mean profile, which is just the brute force addition of all the spectral lines in order to increase the signal-to-noise ratio. Well, this is the intensity mean profile, and this is the Stokes V profile, and this is the null spectra. And as you can see, there is no signal in Stokes V at 10 to the minus 4, which is an order of magnitude better than they had. And this is the results for the other star. And also there is no, in principle, there is no Zeeman signature in there. And just to compare, which is a real signal, this is again the mean profile of this magnetic star with the clear Zeeman signature, and this is the null spectra, which is more or less random noise, which is this one is another order of magnitude lower than this one, the amplitude. Okay. Unless there is no apparent signal in the spectra, we just decided to measure the magnetic field, at least to give an estimate of the upper limit of the magnetic field detection. And this is the theory we used, the so-called weak field approximation, in which the Stokes V profile is proportional to the derivative with the wavelength of the intensity profile, and proportional to the longitudinal component of the magnetic field, so the component in the line of sight for the magnetic field. But of course, what we measure in stars is not the Stokes V profile, is the integral in the stellar surface of this magnitude. So we integrated in the stellar surface, and we got this formula, which is formally the same than the previous one, but for fluxes. So the flux in Stokes V is proportional to the derivative of the flux in intensity, and proportional to the mean average, so proportional to the mean longitudinal magnetic field, which is nothing but the integral across the stellar surface and weighted by the center to limb variation of the intensity. So you can see that if we measure Stokes V and we measure intensity, we can more or less easily retrieve the magnetic field. And this is what we've done. We did it with a least square minimization. This is the chi-square. And this sum goes for a wavelength, which is J, and spectral lines. We did the derivative to obtain, with the minimum of this, and to obtain the magnetic field, which has this very nice and simple formula. which depends only on observables. And this is the expression for the error. And this sigma is the noise of the data. Well, and this is the results we got. Sorry. Okay. These are the results for individual spectral lines in the two planetary nebula. This is the results for the Stokes V and for the null spectra. The same thing as them, we got different results for different spectral lines, but they are consistent with the error bars. And using all spectral lines together consistently, not as they did, we get results that, well, for example, for NGC1360 is plus 100 plus minus 100. So, and this one is 300 plus minus 300. So it's the magnetic field is null within errors. Just here to compare with the magnetic star, which we inferred 2 kilogauss plus minus 71 gauss. So it's a clear detection. So what we concluded is, in principle, the magnetic field is null within errors, but the upper limits are 300 and 600 gauss for the two stars. So, just summary, we have proved that the claim of detection of magnetic fields of Jordan et al. is, in principle, is not correct. So the role of magnetic fields shaping planetary nebula is still an open question. We estimate the upper limits for the magnetic fields to be few hundred gauss, which means that it can mean that, one, the magnetic field is really weak, and then the role of magnetic fields is not very important. Two, due to cancellation effects of the Zeeman effect, which means that opposite polarities of the magnetic field are cancelled. This means that if we have a lot of cancellations, the signal is diminished. So in principle, we measure a very tiny signal, but the magnetic field can be still strong. And the last is that as we measure the longitudinal component of the magnetic field, it can happen also that the configuration is mostly perpendicular to us. So in principle, the signal is also diluted, but the magnetic field can be strong, but perpendicular to us. So, because this is still an open question, we decided to continue studying this in this subject, and we are going to ask for more observation in the VLT to observe polarimetry in the central stars of planetary nebula for different morphologies, and we also can try to measure the magnetic field in the same nebula, but in this case we have to go to very large wavelengths. So we thought that maybe ALMA can be a great opportunity for these measurements. And that's all. Thank you.
Hello, a few comments. One, the first is that it is a pity that we always, also myself, start this presentation telling that the Hubble Space Telescope has discovered, say that, the asymmetry of the planetary nebulae, which is not true at all. I mean, this was
read in the review.
this was not, of course, 20 years before the Hubble Space Telescope. So there is a lot of work done before that with proper classification. So the Hubble Space Telescope simply gave us nice pictures.
Very spectacular, yes.
Okay, but the other question probably are more interesting. One is that, I mean, when we all were aware of this paper of Jordan, we knew that there was something wrong there. So I'm very happy that you found
quite
that,
obvious, yes.
because the spectra were really noisy. And so we say, what is happening here? So you found that what is happening is that the magnetic field is much weaker, in fact. But this is my question, in fact. But the magnetic field is there. because it has been detected in masers, as you have,
Yeah, they are indirect.
and also in the dust polarization in the infrared. So my question is, the measurements of the magnetic fields that we have for sure from the masers and from the dust are consistent, the intensities and the geometry of the magnetic field with your limits?
With the limits? Well, it's difficult because they observe these magnetic fields very far from the center of from the star. So you need to know very well the topology of the magnetic field in order to infer how it lowers down with distance. So I mean, it's difficult. I don't.
So my question is, what is the strength of the magnetic field?
It's very difficult to say because you have to know which is the orientation of the magnetic field. What you get is just the projection in your line of sight. So you have to have a very precise results for telling the magnetic field strength. I mean,
okay, thank you.
Do we have more questions? Okay.
I'm wondering if you could also rule out the strong fields that they obtain by comparing the width of Stokes' eye with what would be, I mean, I know that it's difficult to separate the thermal effects from the magnetic broadening, but maybe you can set an upper limit. Because if the field is
these lines are very broadened by, I think, temperature and maybe electric field, so it's quite difficult to obtain something really reliable from intensity.
And do you know if these authors have done any previous work on measuring Stokes V spectra?
No.
Okay.
More questions? Okay, well, let's thank María again.